we can start again. Again, in my last lecture, I tried to give the main ideas about at least the iterative method for certain class of problems. And this is only for a certain class of problems. As philosophy, I can say, okay, you can do many applications. But Eric asked really a critical question about a problem like a Helmholtz equation with high frequency, for example. It's a totally different things. None of my technique here works. And anyway, fortunately, you have other algorithms out there. They move PML, for example. It's actually, I think it's invented by Professor Jinchao Xu and collaborated beyond Inquest. Those are the methods we applied. Works very well for many class of application. But somehow when the thing getting very complicated, then you have to do all the tricks, which I do not know much about it. But anyway, those are the difficult problems. But what I'm going to choose to talk about here is something we know how to do somehow, and this multi-physics system. If, for example, you do, I've been working with this hydroelectric power generator, artificial heart with many people, and more recently I work with Professor Friedman and his group about, for example, aneurysm, and this all involves coupling of fluid and structure interactions. And one of the CM4 things about is the interface kind of phenomena. Here is an example. So we have the general idea. It's like the question about the Stokes equation. Here we have this coupling between Navier-Stokes and elasticity, and Navier-Stokes equation is already very difficult. Elasticity and all that together. So in order to do the linear algebra right, my take of this problem is you have to understand the model and also the mathematics. After that, you do linear algebra. And this is actually the work. This is out of date. At least. I don't know where I copied. Anyway, this is work mostly this is my former PhD student, Kai Yang. Is he here? Oh, yeah. He's Eric's postdoc. So he did most of the work. So I'm going to use this as an example to illustrate how you can get a complicated problem. You still trying to use the techniques. It's published, right? So why am I doing this? But anyway, I just copy and paste from the wrong file. Okay, the FSI problem. First thing you have to deal with that when you study mechanics, when you do the fluids equation, you just Eulerian coordinate. When you do the structure problem, it's Lagrangian. And like the linear elasticity is really for small deformation and Lagrangian coordinate. Now you have to somehow, well, you don't have to use it. You can do Eulerian description of the structural mechanics, but in that case, linear elasticity may become along linear problems, and you can do both Lagrangian. The fluid just moves too fast. Lagrangian has difficult to trace it. So anyway, so compromise that, okay, I use structure for Lagrangian, but then the fluids for Eulerian. But then how are you going to put them together? One moves around, the other one doesn't move. So when the things on the interface, let me try this thing again. The things on the interface, I don't know if I have a, Oh. So when the sense on the interface, so you have a structure, maybe I don't know. Then you have some fluid. So when this is on the interface, if you use Lagrangian, the coordinate moves together with the material. The Eulerian is fixed. If you do Eulerian grid is. So what are you going to do on the boundary? What are you going to do? So basically, this what do you say? If I what is the next? Oh, I don't have much detail here. But this is called ALE. ALE is that you use Lagrangian of the structure. You don't do it. But the Eulerian somehow, but you won't Eulerian. You won't work with this boundary. So you still do the boundary on the Lagrangian, but somehow you let it smoothly vary. They call this mapping A. So it's what I call a compromised Lagrangian Eulerian kind of things. So you on the boundary is Lagrangian, but it's getting more and more look like Eulerian. They call it arbitrary. Like I don't know where the arbitrary come from, but anyway. So in that case, you have to make some change of variable and all that. So this is going to be in the Lagrangian kind of the solid. This S is the structure side. F is the fluid. This is another Stokes equation in Lagrangian thing. So but this is so far I have not made the change of variable yet. But again, so you have this is the linear. This is the displacement. That's the variable. Fluid is velocity. So you want to take the derivative of the displacement of the velocity. Then you have to make the change of variable the flow type, so that to get the Lagrangian Eulerian to agree. But also when there's a structure, when the surface tension is not a problem, the surface, the stress on the force on the boundary should be the same. This is the interface conditions. And this is a lot of complication here. I just want to give a sketch of how we're going to. In order to do the solver, I want to understand mathematics. So you do this. Let's see. So I have hidden all this arbitrary Lagrangian kind of coordinate. Basically, you make some change of variable. So then you do variation formulation. This one is like a detailed kind of thing. This is like a Neumann kind of thing. When you do the Gaulowski method, the nice thing about Gaulowski method is when this force to be the same, the stress on the boundary is the same. It's going to be like a Neumann kind of things. When you make an integral by part, you do not see these things anymore. You only have to impose this kind of condition. All right, so you have a complicated problems. Okay, this is omega ft. It does moves. Okay, and so you put this h1 function all together. So you do the integral by part, you get some kind of looks like it's a combination of linear elasticity, it's like a wave equation, and now Stokes equation, okay, together. So it's now Stokes equation. You all know it's complicated. You put this together. So so you do this visualization. So we're going to apply the conjugate, the stable like Stokes element to do it. You glue them together. So lots of parameters. Okay. It's a little bit dizzy when you look at these things. But anyway, what I'm trying to say is that if you want to do for simplicity, as I mentioned before, that if the Reynolds number is very big, then you have this convection term. We're going to. I don't want to worry about the convection here, so we're going to make this convection to be explicit to emphasize this. So if in this case you are ending up with something looks like Stokes, with all the complicated looking bilinear forms or norms, and by looking at these things, it really looks very, very complicated. And but there are structures in it if you work hard enough. So it turns out the theorem we proved is that if you have a stable pairs of the Stokes pair, then you glue the elasticity together in a continuous way. So you put them together. Then you have well-posed problems. You satisfy in-soup condition or that on the discrete level. So one of the things is that, of course, it's very difficult to prove well-posed in the continuous level. But one of the exercises we do here is we only solve the linear algebra equation. So it's a finite dimensional problem. The well-posedness for the finite dimensional problem is relatively easier to establish. But the well-posedness is important. As I told you before, that well-posedness problem is this is well-posed means that it is well-conditioned in the continuous level. But here we have not started choosing the basic function yet. So in this case, so we do have well-conditioned problems or well-posed problems. But this requires some proof. Use some fractional Sobolev spaces and on the boundary and all that. But we're not going to. You can prove that in supercondition. Now so what I'm saying is that well-posedness is pretty much saying is you have a chance to get a uniform preconditioners. And then you apply GM rest minimum residual to that. So what I was saying before is that this is pretty much like Laplacian operator. If you have well-posedness for H1, this thing maps to H1 to H negative 1, this from maps to L2 to L2. So when you do the analysis on the analytical level, then you can transform into linear algebra. In that case, you can construct a precondition like that. So it is the inside of the analytical results, PDE analysis, discretization in supercondition, that give you the linear algebra, they name the precondition. For the diagonal, this is like some kind of elliptic operator. This is a mass matrix. You can invert more easily. This is just a preconditioner. And we actually, our paper will prove that the preconditioner system is actually uniform with all these parameters, except one, the Reynolds number. I don't know how to uniform. Theoretically, I don't know any result you can have a preconditioner for non-state equation that is robust with theoretically. I'm talking about theory to prove a theorem. But there are some heuristic methods we can do. But here, in order to prove a theorem, our precondition is uniform with respect to all the different parameters except the Reynolds number. But if we moderate size the Reynolds number, it also works very well. So we have. So Kai did all this experiment. You can see the number of iterations is very robust. But this is compared with this other things, Schur complement, for example, which is probably it deteriorated, but in our precondition it works pretty well. But this is just an example that we use other people's discretization. We do analysis. This ALE is commonly used in the engineering literature. Then we put some mathematics. We try to understand the well-posedness. Once you understand the well-posedness, you can design the preconditioner. The preconditioner would be in terms of some elliptic operator, which we know how to do. Okay, in my previous lectures. So that's one of the. Oh, what is this? So we did some. We have some pictures. Why it doesn't work? What is it? Yes. Oh no, it's not. It doesn't have the file. What happened to this thing? I don't know. What's the problem?
Maybe you can just open the directory directly.
Oh, never mind. Oh, maybe we'll talk. How about this one? I have a beautiful movie, Never mind. Let's just continue. But I just want to show we actually did some real computations. This is a rotated engine, very complicated calculation. So this is the example of the FSI problem. You have oh, wait a minute, I really want to play this so that I can see the interface over there. How do I do this? Yes. Cannot be found.
You should copy your source file to the current folder.
So it's not there, I guess.
Yeah.
Right, you have this file on your hard drive?
But it's okay. I'll skip. Then I have to find it. I have hundreds of files. Okay, let's. Trust me, it's very interesting. But it won't be as pretty as the movie you showed earlier. But anyway, but anyway, so that means also my movie now is going to work later or what? I don't know. Okay, this is the phase field method. So that is the, if you do the interface here, is a sharp interface model. You follow the interface precisely. And one of this phase method is a method that's getting more and more popular these days. I have a postdoc who used to work with postdoc with a Xiaoping phone, and when he came to Penn State, then I asked him to tell me what he's doing. So he told me this. Okay, so phase field method. Phase field. Suppose you have something two phase, and maybe this is a solid, and other one is fluid. So he put a function to be maybe a 1 in the fluid. The other one is a -1. So these are two different phases, right? And so the phase field method, I think the difficulty of this interface problem is this Lagrangian quantity. If you do the Eulerian things, you get a fixed grade, or maybe do adaptive grade. This is a fixed grade. You don't really, Eulerian is easy in some sense. If it's Lagrangian, you have to follow it. Levels at phase field, to put it simply, forget the Lagrangian quantity. Do everything on level. If you want the Lagrangian quantity, take a level set. In this case, you have this. Of course, if you have this is not a sharp interface model. You have you can think a function which is from 1 to negative with a smooth transition down here. Okay. The sharp is smooth, but the derivative is kind of big. Let me see. Every time they kick me out. Okay. So the phase field is that you have this +1, -1. Two different phases, but you want to continue like that. So this width, I don't know, maybe it's like epsilon. If epsilon getting smaller and smaller, your phase field is getting more and more accurate. So this is my function u. So suppose you want, okay, this is an Eulerian quantity, okay? I don't care how it moves. But on one side, okay, I need to tell me the location of the interface. You just find the level set of u equal to 0. Okay. The u equal to 0 maybe somewhere here, so it will be the interface. That will be the level. So the phase field method is nice again, is to forget about the Lagrangian things. But initially you have to know. But level set method is also the same thing. So level set method again is the Lagrangian quantity. You simply introduce another function they call level set function. Here is the phase variables. And so then the interface is gone. No more interface in your computation. Okay. Then you have to figure out how to do it. Okay, for example, this mean curvature flow. If you have the normal velocity is kind of proportional to the mean curvature of the curve. If this means that if you have curve to be, I don't know, if something like that. On this point, the curvature is big, so it moves faster. And this is the mean curvature flow. So that's all the flow property. Suppose that's the current mean curve. But in the levels, in the phase field things, it's this Aron-Kahn equation. Can you visualize these two things are the same thing? when let epsilon approach to 0, this solution of this one actually approach to that one. That's not a trivial thing. But well, I don't know whether Aron-Kahn originally did this or not. But I don't know much about the history. But mathematically, at least, when epsilon goes to 0, what is UFU? It's U cubed minus U, or U cubed minus U. So this one, when epsilon goes to 0, the levels of U will approach to that curve. That's the mathematically can prove. So now, this is a odd-looking equation in terms of mean curvature. All of a sudden, it becomes an elliptic equation. And isn't this beautiful equation? You just call your favorite software. You can just compute. Any point, okay, I need the level, need the phase, the interface. Okay, let's get the level set. So this is a hit equation, looks like it, but this long linear term is the whole story. Okay, it's a long linear term. Now the thing is that when epsilon is this long linear, and it oscillates, it's not a monotone. This thing. If this one is a monotone, the derivative is positive, then you can do it. Or the antiderivative is not convex. It's called double wave thing. And this will be about an equation. When epsilon is small, this problem becomes difficult to solve. So then you have this Heron-Shaw flow. This has to do with the Stokes flow Kahn-Hiller equation. This is two. Maybe just do Aron-Kahn equation. Aron-Kahn equation has this property, and you have this energy. This would be involve some interface kind of situation. If on the penalized, when epsilon equal to very small, U will be most places U square should be equal to 1. Right? It's plus or minus 1, right? Then you keep the phases. And you can prove this energy law. This you call this Aron-Kahn energy. In particular, this long negative term, this energy is actually monotone decreasing. When T is getting larger, it's getting smaller. This is actually called this energy stable. Energy was, you can do the same thing with Kahn-Hiller. Again, the phase field method is the Lagrange quantity of the location of the interface is transformed into Eulerian quantity. I think one of the nice property of the levels, the phase field is very easy to code. If you don't care about accuracy too much, you can just code. And but it is there's no free lunch. If it's something easy, the other things are difficult because the epsilon is small. You cause some difficulties. Okay, are we on the same page right now? So think about the mean curvature flow. The normal velocity on the boundary moves faster if it's sharper, if the curvature is bigger. That's the level mean curvature. So it's somehow it's kind of approximated by this Aron-Kahn equation. Now Aron-Kahn equation is a totally Eulerian quantity, so you can code this up in a matter of hours, or if you depending how you call anything. Now there are issues here. And one of the now you want to. So I was asking my postdoc Yukun explained this to me. That he was telling me that okay, the fully implicit scheme. Okay, one of the things. Okay, you want to study this is a fully implicit scheme. About it is conditionally stable. This is when you have this. Usually we say that when you look at the linear scheme, if the fully implicit scheme is unconditionally stable. But this is a non-linear problem. The energy stability is not quite like this stability in terms of lux, or maybe for Neumann, that kind of stability. But nevertheless, for fully implicit scheme, It's not an unconditionally stable energy-wise. You have to have k be sufficiently small. Okay, if it's a non-linear problem, all right, it's not really the linear stability. If you have a result like this, that's fine, I accept. But the next is, he told me that surprised me. There's something called a convex splitting scheme. Convex splitting scheme is that is a partially explicit to make this guy is a bad guy. Well, even though this is a linear term, that makes the things non-monotone or non-convex, depending how you look at it. So make this one to be explicit. Okay. This is called convex splitting. I actually would call a monotone scheme, monotone splitting, because this is a function which is not monotone. It's a difference of two monotone functions. If you study real analysis, any function can be written as a difference of two monotone functions. And but if you take the antiderivative, that means any non-convex function can be written as a difference of two convex functions. That's called convex splitting. But anyway, they call it convex splitting. If you think about any department, it's convex splitting. If you think about really different, it's kind of monotone splitting, whatever. You make this a non-monotone one. But the nice thing about this one that is a convex. If you take the derivative of this one, this becomes a major particle definite. This is a very popular convex splitting scheme. Now you talk about stability. The most surprising thing to me is that this scheme is energy stable is unconditionally. Newton method is a convergent. We're talking about solver, not a linear solver, non-linear solver. So in most of the convex, this phase field business, convex splitting scheme is the most favored method. Because that again, if the Newton method, if you take the Newton method, it's a Jacobi, the U cube take the derivative become U squared. That one is a positive term. And the Newton method will converge globally. It's beautiful. Isn't this really remarkably beautiful? Unconditionally stable. But it is it's an explicit scheme. And do you believe this, sir?
It's strange.
Anyway, did you listen to my previous slide? If you do fully implicit, it's conditionally stable, energy-wise. If you do partially explicit, it's unconditionally stable. So I work with Shu Lan, and this is his other. We'll work with together. The three of us in my house. When I jumped out of my desk, I don't believe it. So come on, this is.
So there's still a part that's implicit here.
Huh?
There's still a part that's implicit.
But at least it's not fully implicit. A partially implicit scheme is unconditional stable, although and the fully implicit scheme is conditional stable. And because of these things, it's really, this is actually quite amazing. Actually, it's unconditional stable. So it's many people like these things. Now the question is that how come a partially explicit scheme is more stable than a fully implicit scheme? Or partially implicit depends how is the cup is half full or half empty. But anyway, so they are. This is where I got interested in these things. I want to understand it. Okay, it's not really a paradox or anything because it's a non-linear stability. Energy stability is really different linear. But nevertheless, the fully implicit scheme should be more stable, right? At least that's how we gotta educate ourselves. So let's take a look. Why is that? So this is the partially implicit scheme, okay? And so I'm going to rearrange things. I put a minus plus thing, okay? When I do solve it, all these things, anyway, I just want to do some mathematics. Okay, we want to understand this game, okay? So this is the first step. The second step is that I'm going to, this term here, this term, un minus 1 is also here. I'm going to group them together, okay? Group them together here. So this one is a fully implicit. But I have this extra term here, epsilon squared here. If you like to do that, if you think about this like 1 over epsilon prime, k prime, I have a fully implicit scheme with a different time steps. You get it? 1 over k prime equal to this guy. This is because epsilon is so small, this one is much smaller. The k prime would be much smaller than k. And k prime is actually less than epsilon squared. If you look at the things here, because this one is less than 1, k over this guy. So the conclusion is that this convex splitting scheme is equivalent to a fully implicit scheme with much smaller time step size. And this time step size is precisely the sufficient condition for this scheme to be stable. So it's unconditionally stable for any k is because it's actually equivalent to a fully implicit scheme which has extremely small time step. At least this explains it. Okay, at least then I can go to sleep. But the thing is that it's just mathematically. This is what at least you understand why the convex splitting scheme is actually more stable than fully implicit scheme. Again, it is a fully implicit scheme with extremely small time steps. The thing is that if you do these things, you can actually say, this one I call it delayed convergence here. The interesting, the convex splitting scheme is always, when you compute, is qualitative always correct. This is the only thing that because k prime is less than k, if you think about it, even if you think about k, right? Okay, you have to, for me, I trust the fully implicit scheme better. Okay. If you trust that, but you can also numerically verify the fully implicit scheme is indeed very good, except it just is. And now, so the k prime is for the convex splitting scheme has a delay is much smaller than the real things. You are just starting from k. You're thinking you're solving for n times k, right? This is the things you are thinking you're solving. But if you trust the fully implicit scheme better, you are solving nk prime. So this is much smaller. The theta is delayed. Even for the extreme case, even the k epsilon square, the convex splitting scheme is if you think k approaches infinity, it's half. If you're solving the problem in 1 hour later, it's still in the half hour region. Even for very small time steps. But when you look at the pictures, you never detect this problem. If the physics is all correct, it's just the time scale get changed. So the qualitative is correct. The quantitative, if this is like if you don't. But anyway, we can actually do numerically. You can do it exactly. Anyway, this is again the joint work my postdoc Yuquan and also Sholan said that. And then they did all this computation. As you can see, that fully implicit scheme is you get a much delay. This is you have a disk which is shrink. This is look at the radius of the disk of the face. That's the radius. This is a fully implicit scheme. This is other schemes.
Which is the order is the same for all methods, or the order is the same, just a constant, or different orders?
What order?
The order of the method.
This is I'm talking about the Eulerian scheme. You're talking about that order?
So they're all first order.
This is first one. Now this is a good question. When you go to second order, this phenomenon is not so obvious. Then the second order scheme actually turns out has other problems. These are the things we have pictures, not here. But anyway, we did the computation. Basically, we actually found the second order scheme. There are many stories behind these things. The second order scheme is actually, it looks beautiful, but you get the wrong physics. Because we're talking about the second order scheme we tried, actually, you get a very bad. But anyway, second order scheme, you got a less delay, but you get the wrong physics for more general problems. I'm not an expert of this. I only started to work on this a few months ago. Because there are people doing. You want to do multi-grid, you want to do solver, right? But for me, you want to do a solver. Which equation you want to solve? So I want to understand. For the convex splitting scheme, is beautiful. You have the convex problem. You can do the multi-grid over that. But for Fourier implicitly, I don't know how to solve. And but anyway, I should get distracted here. But the thing is that, okay, first of all, the convex splitting scheme is qualitatively correct. There's a significant delay. Otherwise, it's okay. For example, you can actually say that if you think about it, is the convex splitting scheme is actually a fully implicit to do a perturbed equation with a perturbation here, which causes a delay all the time. And anyway, second order scheme, you have such a perturbation. Here you have the same. So the message here is that convex splitting scheme is still a good scheme if, but you have to know there's a delay there. Okay, that's one thing. The second thing is that the fully implicit scheme to be conditionally stable is not too bad. To capture the physics, since I just want to use a philosophical argument. Since the convex splitting is liked so much by many people, so so that means I can also do fully implicit scheme with a very small time step. They are equivalent, okay? Now the question is that in that case, you want to, how do you solve the fully implicit schemes? Is the solver business. So it turns out I want to prove a theorem. So you remember that to prove a theorem for this thing is very difficult, but we managed to prove something. So the phase variable is between -1 to 1. This is really the phase variable. You can prove that the continuous level is between -1 to 1. But so this can be proved. You can do the maximum principle kind of argument. But on numeric level, how do you know it's true? So actually it is not true in the numeric level. For first order scheme, actually it's not too bad. The violation is not too bad. The second order scheme, the violation is huge. Because we know that the monotone scheme or the other positive is only lower order does a good job. Higher order never do a good job. This is generic phenomenon. This same here is true. If you do second order scheme, that our observation is that this phase variable go wild. But if you look at the level set, you still get beautifully moving things. Except that if you do a good scheme, we don't have a picture here. If you do these things here, if you put these two moving together, they are totally different things. And so, if you want to do phase field, if you really care about the accuracy, it's very subtle business. But okay, I just want to prove some theorem. I'm looking for these things. So I want a scheme that preserves this property. Okay. So in this case, the idea is the following: how do you change your scheme? Basically, if you think about it, piecewise linear functions. If the piecewise linear function, you do the test function becomes quadratic. Okay. Then you do an interpolation. This is like a Max-Lampian. Okay. That's precisely similar to Max-Lampian. you do a linear interpolation. This one you have a cubic polynomial multiply linear polynomial because the quartic polynomial. You take a linear interpolation. You do that. If you do these things, then we can prove that this one's this one this phase variable it is between -1 and 1. Then you can prove these things. Now, once you got this one, now we can actually do a rigorous mathematics. So now you do first of all, k over epsilon square should be less than 1. This is the condition where the convex splitting scheme give you. It is really a necessary condition, in my opinion, to get this business. So you have to have very small time steps. But also keep in mind when you do the phase transition of the phase kind of business, usually it is changed very rapidly. The time scale is actually very rapidly changing. So if you take that into account, this is not a big. But for mathematician, you don't have all the other parameters in there. For this is not really a very restrictive condition. But you have no choice. My claim is that the fully implicit scheme, you have small time steps. You have to do that, I think. Otherwise, you don't get the physics. Now, once you get this right, if this at least is my understanding right now. If you get this right, then you can do multigrid beautifully. Okay, we can actually prove a theorem. You can do precondition. You can prove this one in very rigorous mathematics. But again, wait a minute. I have some reference by. Where's the reference for what other people did? We don't have a reference here. There's some people like your advisor Stephen Wise. Some other people did some multigrid, but. Here I prove a theorem, okay, so what the difference is. But I have to change the scheme. Wait a minute, where's the reference? Paper, at least you can go, this is archive. So we can prove these things, we can prove, but it's a little bit technical. But anyway, so in order to do a good solver, the way I see it, I have to understand the model and also the numerical schemes. Once you understand those things, then you can design good solvers. And this one is this long linear term is very dominating all the whole things, and you have to treat them very great caution. Even though when you apply this thing, have a beautiful picture, doesn't necessarily mean that you get the right physics. And it's very difficult from. I do not feel qualified to say too much about the convex split, all this phase field method. But for this particular problem, this is what I can say rigorously, mathematically. So, but of course, usually you have to think about adaptivity on the integral. You put a refinement there. Then, if you do that of a multigrid method, converges beautifully. PCAG converges beautifully, uniform. So this is an example of how do you do solver for a particular problem. The last problem, FSI, is complicated in some way. This is a very naive-looking equation, Petty equation plus a long linear term. But the long linear term with a small parameter causes you difficulty, and you have to take into account the accuracy of the physics. If you get those right, then the solver becomes easier. So my problem, even the analysis. So the discretization, we did this monotone. This maximum principle kind of preserved kind of scheme, so that you get the correct discretization, both in space and in time. Then we can do the right solvers, and with rigorous mathematics. This is a two-phase. And another thing is that I don't know what time half hour. So multi-phase is something which again is with a short line, and this has to do with George. George is not here today. George is sending me this paper, one of this paper for me to review in JCP. I said then I said, okay, I don't know anything about the phase field. Why you ask me to do it anyway? So he's the boss, right? I have to do it. So So I was reading these things, I couldn't quite really understand it very much. But I found one place that is saying that the well-postness has to do with the coefficient matrix. I'm going to explain to you later. It's a positive definite. And that's a beautiful result. But the only thing is that here it could only prove it numerically. I actually thought, okay, maybe I should be able to prove it. So I wrote. Anyway, I probably should say too much about this. Anyway, I made a suggestion, but somehow turns out the proof was not right. What I suggested. But then we came around in the shoreline, get an idea to how to prove these things. So this phase, the characteristic, this is a model which is, by the way, it is in this paper. So we don't have it is a model by in this paper, and here we're doing here the assumptions of this thing that if you have multiple, suppose it's 4 phase. If you look at the things that every 2 phase meet, this 2 phase, if you look at this locally, it will recover the 2 phase model, iron count model before. Okay, does that make sense? You look at it locally, and then you should recover the original 2 phase model. Of course, you have multi-phase situations. You have the characteristic function, which is in this region C1 equal to 1 equal to 0 outside, this C2 equal to 1, and all that. So this is the basic assumption in his paper, Steve Dunn's paper. Now the thing is that then you can think about it, maybe do the phase variable, you make a change of variable. This is the characteristic function. This is use a phase variable. And you can many different phase variable. For example, in this 2 phase situation, you can make this change of variable. You make this change of variable. So you become this 2 phase model, which is the iron count of the model. Now the thing is that how do you? So now you remember the assumption is that if you look at the locally, if it's 2 phase. Now that's what we do. If you look at only look at the 2 phase. So CK plus CL, K and L, they meet together, all right? And you have to do the 2 phase, the other place are 0. So you look at the energy density functions, you'll find, then you go back to the original iron count model to make the comparison. But then one thing which I didn't say is that in this iron count model, earlier that we don't have the surface, we don't have the other parameter. There should be another parameter that's called lambda, which has to do with the surface tension of this the things between 2 phases. And if you compare this together, you end up with this algebraic equation. So the 2 things you want to do, because you give the surface tension, so then you get all these different coefficients. There's 2 things in order to have the well-posted. Number one is that you can find this AIJ. You can find these things. Oh no, the AIJ is given. You can find the existing lambda IJ. That's one thing. Secondly, this lambda IJ. This is one of which is observed by Steve Dunn. That he observed that this lambda IJ is actually positive definite. If you get rid of the 1 phase variable, but if you do the all semi-definite. So you want to solve this linear algebraic equation, which in this weird form. And to solve this one is not so obvious. But anyway, this thing, it turns out, we have a colleague in Peking University, Jinchao Xu. At that time, he actually proved the following result. If you take a symmetric matrix, okay, if you think about symmetrical matrix, n by n symmetrical matrix, that's a linear vector space. Okay, this linear vector space is I think the dimensions n, is just a symmetrical matrix. then he can actually identify a basis function. A basis function, if you think about this like a 3x3 matrix, the basis function is actually, if you look at the tangential direction, is the tangential direction. This is like this is the tangential direction times its transpose. This is rank 1 matrix, symmetric. If you take all the edges together, it forms a basis. This is what Jinchao Xu's result. He was doing some elasticity equation. This is a beautiful thing in his paper. That's actually about the same time which Shonan made the was reading that paper, and then there's a connection where you can use the result to prove the existence of this linear algebraic equation. And but the interesting thing is that under what condition this thing should be positive definite. In the three-phase cases, it's this in the literature. If you have a three-phase to coexist, okay, you have a triple point. The surface tension matters. You cannot just say to any surface. If the one of the surface tension much bigger than the other, things will push through. If there are three phases they meet together, it turns out the surface tension should satisfy the triangle inequality. I think this is known in the literature. So under this condition, three phases should be. It turns out for these things that would be positive definite. But for the phase which is bigger than 3, which is unknown. So in this work, in our studies, this would be this is the same for n greater equal to 4 or not. It turns out in our analysis this is not the right condition. Each one of the sum is bounded by the triangle inequality. And it turns out the theorem is the following. If you have 4 phases, the phase is well posed. If you have a pool of 4 phases and 4 vertices, and you have all these edges. If the pairwise surface tension can be viewed as the length of the edges of the subplex, then this one is well posed. So you have n phases to coexist. This would be the condition, but there's a physical argument about this condition. But this is mathematically derived. You still need somebody who knows physics to argue this is the right condition. But at least mathematically, we can prove that. But anyway, what I'm trying to say is that if you do n phases, if you get the mathematical right, then everything about this 2 phase can be generalized to the n phases, and so you can do a n phase Allen-Kahn, this Allen-Kahn, do Kahn-Healy equation. Then you can do all the discretization. You can do the fully implicit scheme and convex splitting, Kranko-Nicolson scheme, and all that. And so you can generalize in a very straightforward to multi variables, multi phases. There's lots of details here. Then I don't know if this one plays or not. Oh, this one plays. This is a green. This is how many phases? This is a 4 phase, right? 5 phase. 5 phases. And even though the picture looks very pretty, but the accuracy can be very subtle. but I believe we got it right. But all the energy function, all the things. Anyway, this is a triple point. This is actually 4 phases. So initially, well, I don't know. How can you put a four-phase like that? This is some phase out there. As you put the surface tension. If you put the surface tension between all the things in the same way, it's going to end up with a very symmetrical configuration in the end. Okay. So now, if you have the surface tension, one is bigger than the other two, this thing will push through. It becomes unsymmetrical. And again, this four-phase has to satisfy this simplex condition. Otherwise, this model is not well posed. So you can argue that this model has a limitation. Okay, but this is it actually changes pretty fast. This is for all the surface tension about the same. This one, this surface tension is bigger than the other two. This surface tension is bigger than this other two, and the steady state. For here, you do the multi-phase, you do the correct mathematics, then you can solve all these things very similar. But the one thing we couldn't quite do is that when the M phase is, because there are several variables, this Maxim principle, it cannot be proved. You know that the Maxim principle in PDE usually is only true for second order scalar equation. If you have a system, higher order, the Maxim principle cannot usually be proved. And that's the open problem. But you can actually, maybe it can be proved, I don't know, because you have there are sometimes that the couple the second order equation in some special way, you can still prove the Maxim principle. But this one we have not explored too much about it. But it's that's the multi-phase. So we're talking about the first example which I did with the Jiangkai is about FSI problem. That's using ALE kind of approach. You have interface, which is a sharp interface model. So you have different that kind of mathematics. For phase field, it's very popular method, a very very useful, powerful method. So we look at some issues of it: the convex splitting, the implicit scheme, the relationship, and so then we can do some solvers issues. If you understand the discretization, then you can you can get the solver according. And you can. Now we then for the two phase, you do the multi-phase. They have this model by Steve Dong. And he numerically observed some very nice property of the model. We mathematically prove it. So then you can, with that kind of mathematical results available, you can design all these schemes similar to the two phases. That's how we do. I use this example to demonstrate that when you do solve it, or that you cannot just take the equation this way, then you do it. In order to do it, you have to somehow, for me, I have to understand it somehow. When you reach some level of understanding, you can do something. The PMP equation is something we have been working on. And again, there's lots of we have many people CM4 project has been working on it. We trying to do some analysis. For example, my former postdoc, he worked on he was part of the CM4, but he left for a company. We wrote a paper in JCP. We can discretize again. This have the energy stable. It's like what I said before. So before we do the solver, I want to understand the same kind of approach I will take. I want to understand if the discretization is done the way I can. So in the PMP equation, there's energy law, very rich mathematical structure in the PMP. But if you put a DFT there, then I don't know much about it. So but at least the PMP equation has a. So we actually devised and analyzed many energy stable method. We've been also doing this the solver for this problem, and it seems to work very well. Except that if they have this epsilon here, again it's a parameter like the epsilon value. If epsilon is getting small, have you guys similar difficulty? If epsilon is small, then all the solver will have problem. Nonlinear iteration would deteriorate. And you maybe have boundary layer, things on the boundary and all that. One thing is Arthur, he's working on the things. We're hoping to use this technique which is developed by people like David Case, Xiaoquan Cai in the domain decomposition community. It's called the nonlinear preconditioner. We're actually working on it to try again to understand the things in a more abstract way. To what is this nonlinear preconditioner really doing? So we have done some. The author has done some analysis. This nonlinear solver is something I haven't talked very much. I just linearize the problem, you solve the linear problem. But again, this preconditioning technique can also do the things on the nonlinear level. And you do you precondition the problem before you linearize it. Then you go from there. So this is something we are working on. Hopefully we'll get to an iterative method. The Newton method will be robust with respect to epsilon. For the linear problem, if I do the discretization correct, I do not worry too much about it because I know a few things about linear solve. The nonlinear problem, there are issues involved. There's lots of nonlinear techniques. But anyway, since the mathematics, the physics behind this things, I think the PMP together maybe coupled with Navier-Stokes equation, all the other problem which is CM4 is interested. And I see lots of structures in it. We're hoping that we can also do the some techniques to be used to speed up the nonlinear solvers. I use this example because there's lots of technicality here. But again, maybe next project report meeting I can talk more details. So these are the several examples I used to describe a solver you can do for the complicated realistic problems. And we actually also try to develop this academic solver package. We actually have what I call a FAST. The framework I said is a fast auxiliary space preconditioning. If you think about the technique we have been using is that if you have some sub problems, and so the idea to make the problem robust and efficient is that you have to think that if the original problem is well posed, when you do the linear algebra, you make a well posed problem to be ill posed problem. Well conditioned problem to ill conditioned. This is because of the way you choose the basis function, for example. And so then you can think about multi-grid domain decomposition or any other technique mathematically. You can bring them in to make the problem better conditioned. I use but anyway, so this is a generic technique. What I actually think is that if you have a well-posed physical problems, so the chances that we have good precondition. Our idea is of this FAST is to put what the new algorithm we have up there in not the sophisticated things you guys do, but I want the proof of concept kind of algorithm there. And we actually put many solvers. There's a web page there. Anyway, we have IRU, AMG, geometrical multigrid, and You can use all different kind of AMG, and then you use the things, you put them together. It's not it's not a black box. Well, we probably going to call it a gray box, or what some people call. You use a special structure. All the method I talked before, FSI, phase field, I don't know, PMP. It's not just blindly to solve these equations. But hopefully, your solver would not depend too much too much of these things in there. Otherwise, it makes the solver not user friendly. And anyway, so this is our package. We had example of complex fluids, FSI problem. We actually done a lot of things about reservoir simulations, and of course we can do any Maxwell equation. One of the things we spent a lot of time, I wrote several papers with my students recently, the MHD problems. The fuel cells, all these things we have used. But anyway, this is the kind of thing we just put there. Hopefully, we can grow, and if people are interested in trying to try it out, you can go to our website and you can contact us. And okay, so I talked about in the first lecture. I talked about the idea of doing iterative method. When you have the complicated physical problem, they have different all kind of issues to worry about. With FSI, with the Yankai, we did the analysis. After the analysis, you can do the preconditioner. We use the phase field method. This convex experience again very interesting, but it has a close relationship with fully implicit scheme. And then to solve the schemes that we realized that the maximum principle, in order to really do things rigorously or do it right, the maximum principle plays a role. So in that case, the first order scheme actually seems to be more preferable. And so for the end phases, we started some other people's model, like the Steve done. This is just a model. There are many models, which I didn't know too much about it. For that particular model, we proved the well posedness together with shoreline, using some very recent mathematical techniques. Once those well posedness is established, you can do discretization solvers accordingly. There's lots of open problems still. With that, this is already last page. Where's my thank you note page? Thank you.
Okay, any questions?
I have a question.
Yeah.
If you go back to the PNP, so what do you have there in the figures?
So this is something that Max-Medi computed with different kind of data. Arthur, you know this picture? Huh? Sorry.
I'll look at the paper.
If you ask me about a theorem,
I guess it's a channel. You have low velocity, some charge. So you have the most charge. Density is a value. So what's the
What does it mean?
in case of the problem?
Okay. All right.
I think it does can corresponding to
So
some.
this is with the energy stable finite element.
Yeah. I think we use these things. I think Marx he did this using some of this benchmark problem, the data from the paper, and we want to see the test of the new scheme we started, which is energy stable. And there's some special nonlinear term. It has to be done in a very special way. So my belief is that if you do the discretization right, you have a better chance to solve it more efficiently. And
once you do the finite element discretization, then you have a system of ODEs.
Right. Okay. It's like all the other problems, right. But it's an ODE with lots of structures in there. Yeah, but it is a phenomenon in this boundary and all that. One of the things mathematically to say that most of this physical problem, even PNP, I suppose, the things change more rapidly in some local regions than other places. Those places where the nonlinearity that dominates. And this nonlinear precondition is that, if you do the Jacobi in a global way, this local problem slow down everything. And so the idea is that you before you do the Jacobi you solve this local nonlinear problem.
Okay.
And so you reformulate the problem so that under the assumption the local problem is solved. The local problem is still very difficult problems because it has all the nonlinear problems, but it's much smaller problems.
Okay.
So I think this really makes sense, but they have been working by the domain decomposition. It's a small group of people. We hope to understand what actually the mechanism that drives these things. If the nonlinear phenomenon is everywhere, then this is not going to help you very much. If they have some local phenomena, which usually I suppose in engineering physical problems, are sitting somewhere. So you solve the local nonlinear problem. It's still a difficult problem, but with a much smaller number of unknowns. And there you use brute force. So then when you do the outside the Newton iteration, then the number of iterations will be much smaller. So I'm actually hoping that this PNP, I don't know about your DFT things, but we want to demonstrate for the PNP, I'm pretty optimistic. This will give you some good nonlinear solver. And we especially want to be adaptively. I don't want to know too much about it. You go there to detect the local regions. So in the finite element community, there's lots of work about adaptive finite element methods. We're hoping to use those techniques to put it here. So this is our kind of ongoing effort. And I believe there's a quite good potential here.
So in one thing you say, you talk about the energy stable finite element discretization.
Yeah.
You say now that you want an adaptive finite element. So how do these things reconcile with?
So the finite element discretization scheme, which the adaptivity comes in here has two meaning here right now. Number one is that the adaptivities have two things. One is that for this region here, you want to do local mesh refinement. That's one thing. So finite element scheme is still the same scheme.
Okay, so you use the same finite element scheme, but you go
different grid.
Adaptive refinement locally.
Yeah.
Solve the
this is the accuracy part.
Okay.
There, but the nonlinear problem have not adaptivity here. This is something new we're working on.
Oh.
So I want to adaptively detect where those things are.
Yeah.
And we still have not fully understood what is actually the mechanism to speed up the Newton's method. That's another part of the adaptivity. To detect the nonlinear dominating regions. So you group them together. Hopefully it's not too big. So then you do a nonlinear pre-condition by solving the local problem, the brute force, or maybe some other method. But instead, you don't. It's like the other nonlinear problem. Ooh, you solve the big, gigantic. So the nonlinear iteration will be lot, but the local problem, nonlinear 100 iteration, I don't care because it's a small problem.
Thank you.
I have a question. Can you show the page you on your FASP solver, like the different capabilities? So I was just curious, so what exactly? So the package is basically, so it's just the solvers, right?
No, we are actually doing this. This is still a preliminary thing. So we actually we have solved all these problems.
But so it's
The code is.
the PD solver and the linear solver.
We have the components in the package that can be used to solve these things. But we do not have it's not a black box thing. For this one, we do have the solver ourselves. So this is the application of the FAST.
Oh, I see.
And
So how does it compare with the Hyper or such solvers?
Hyper, which I was.
Or SMG?
Okay, now I can tell you all that. Hyper is a wonderful AMG solver that they also implemented my Maxwell solver in there. But they are mostly for symmetrical positive deafening problem. And that's what we said. Some of these things we just call Hyper. If you're talking about multi-physical system, which actually Chinino, by the way, has all those things. Here we want to stay. First of all, you should be able to solve a multi-physics problem, and we also have our own AMG. If you talk about SAMG, that's a different time of AMG for maybe you're talking about the German group.
Right, the German is running for it.
But even I'm actually writing a survey paper for Octal numeric right now. So if you ask me a year ago, I may not be able to answer, but now I can. So I've been doing all this AMG business. So that's a very nice AMG things. But I'm here. We have we solve we have most of this algorithm. But while I come here around, at least my motivation is that it's not a totally algebraic. You're going to use some grid information. Like this AMS is what I call a hypercore using my precondition with a flipped mile. That's not a purely AMG method.
Are you talking about SMG or FASP?
I'm mixed many different things together. Hyper, for example, the elliptic equation solver is purely algebraic. You give a matrix. But their Maxwell solver, they use my algorithm. They have to use the grid. You have to have the grid. And we are more, we sometimes use their method, we have our own method. But mainly, I'm hoping to put, this is what I learned, that the reason the Lawrence Livermore group, Hyper group, were using my method because I want to give a talk. And they couldn't quite, they find it very interesting, but somebody actually understood it's actually Zania and Panaya, they understand my algorithm, they implement it. And they really made it very efficient. Then I actually realized, right? Then I was joking that I have like maybe 10 or 20 more algorithms out there, why don't you use it? But the reality is that nobody really uses your method. So, okay, I do it myself. This is the main idea. So I would have some algorithm which I love. The other people probably couldn't get. They said that it takes probably 20 years. Somebody told me that. You have a beautiful algorithm sitting there, and maybe 20 years later somebody use it. So I want to speed it up. So if I have some algorithm, I just want to put in the fast. So it's more cutting edge things. Hopefully for people, professional programmers, they can with some proof of concept example, then they can probably use it. And so I do believe that many problems there are. At least in principle, we know how to do it. But it's very difficult to convince other people to use your method. But I think we are lucky that day I gave the talk in university because they are doing MHD, fusion, fission, the kind of things. The physicists want to do it, they understand my algorithm, and they went out to implement. But that's very rare, that situation. So you just have to implement yourself. And that's what kind of, at least my original, but now I have a big group for doing these things. Now we have many different ideas. But we don't have that resource like you guys have to have. Well, maybe. Yeah, but anyway, hopefully it's going to be something. Eventually, maybe maybe the hyper people can know that maybe they kind of take some of the things to make it into their code. This is more academic exercise. So.
Okay, all right. Well, let's wrap it up. Yeah, thank you.